It's been 4 decades of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system.
Since 1977, NASA's Voyager 1 has been cruising across space. However, scientists did not anticipate this. Now 14 billion kilometers beyond Earth, the old spacecraft recently accomplished an unthinkable feat. It took a different course on its own. Even more unsettling, it began sending strange signals with patterns that experts are frantically trying to figure out just before it turned. Insiders are panicking, but NASA is remaining silent. Does Voyager have a message for us? Did it discover something in the dark that altered our understanding of space? The unforeseen signal. Dr. Margaret Chen startled upright in her chair on a Tuesday before dawn in 2023. The 73-year-old engineer was a young graduate student when he originally joined NASA's Voyager program in 1972. She looked at her monitor in shock now, some 50 years later. The farthest man-made object in the world, Voyager 1, was returning signals that it had never been designed to convey. The spacecraft, which is now more than 14.5 billion miles away from Earth, had been returning consistent data on the interstellar medium for years. It was different tonight. There was a subtle rhythmic pattern hidden in the mundane information. A mathematically accurate low-frequency hum. Random interference was ruled out because the signal remained constant throughout several broadcasts. Even more concerning was the fact that this enigmatic hum had surfaced only a few days prior to Voyager's unplanned trajectory change, which no one at NASA had ordered. Chen's coworkers huddled around her desk, while the fluorescent lights pulsed overhead. Although the computers were sleek displays instead of room-size machinery, the room still had the same smell of electronics and coffee that had dominated mission control since the 1970s. The unusual signal pattern pulsed with disturbing regularity on the screen. Jimmy Carter was president when Voyager 1 was launched. The Apple II computer had just been released, and Star Wars had just debuted in theaters. Now, it took more than 21 hours for the signals to reach Earth at the speed of light. A person could travel half the way around the world in that amount of time. What had Voyager found in the empty space? Why would a spacecraft that was built to stay on course through the distance between stars change course? The expedition, which started out as an investigation of outer planets, had transformed into something completely different, a mystery at the edge of interstellar space that tested our knowledge of the universe and possibly our role in it. Experts from many fields gathered in a safe conference room at the Jet Propulsion Laboratory in Pasadena as morning broke. The questions were deep and lingering. Had Voyager 1 come upon something we couldn't comprehend? Was this the first discovery of something groundbreaking, or was it a technical error in outdated systems? Our perception of interstellar space, and perhaps of humanity's isolation in the cosmos, might change if we knew the answer. The beginning of a great adventure. A unique cosmic alignment marked the start of the Voyager adventure. NASA astronomers recognized in the early 1970s that Jupiter, Saturn, Uranus, and Neptune will shortly align in a way that only happens once every 176 years. An unusual opportunity was presented by this planetary lineup. In a single voyage, a spaceship may go to all 4 outer planets, using the gravity of each planet as a slingshot to move on to the next stop. The first time this concept occurred to Gary Flandreau, a young engineer at JPL, he was using a circular slide rule to plot planetary positions. His discovery created a beautiful grand tour of the outer solar system out of what may have been separate, expensive expeditions. The Voyager program, which consisted of 2 identical spacecraft entrusted with exploring Jupiter, Saturn, and maybe beyond, was a scaled-down version of the Grand Tour, which the Nixon administration had originally canceled for cost reasons. Standing 13 feet tall and featuring a 12T dish antenna as its face, each Voyager spacecraft resembled a massive mechanical insect. To protect delicate magnetic equipment from the spacecraft's own electrical disturbance, a lengthy magnetometer boom protruded like an insect's proboscis. Cameras, spectrometers, and computers with less processing capacity than a contemporary digital watch were housed in the main body. 3 radioisotope thermoelectric generators powered the entire device, which weighed 1,820 kilograms, or roughly the same as a compact vehicle, and transformed heat from decaying plutonium into electricity. The establishment of the mission was not without controversy. Budget watchdogs questioned the cost of sending probes past the recognized edge of our planetary system, while environmental groups denounced the deployment of nuclear material into space. However, Voyager 2 launched from Cape Canaveral on a Titan II IE Centaur rocket on September 5th, Voyager 1 following a quicker course that would enable it to arrive at Jupiter and Saturn ahead of its sibling. The exploration was supposed to span roughly 5 years, according to mission planners. Rather, they produced our first real interplanetary travelers and the longest-running space mission in human history. The engineering difficulties were enormous. Creating systems that could survive deep space isolation, temperatures that are close to freezing, and decades of cosmic radiation. Above all, with communication delays ranging from minutes to hours, the spaceship had to operate with ever greater autonomy. A special cargo, the Golden Record, a gold-plated copper disc with sounds, music, greetings in 55 languages, and 116 photos from Earth, was developed by Carl Schahn and a group of scientists prior to the journey's departure. These documents, which were affixed to every spacecraft, served as a message to the universe and a human time capsule for any intelligence that might come across these lonesome Earthlings at some point. Planetary disclosures. In March 1979, Voyager 1 arrived at Jupiter, starting a period of exploration that transformed planetary science. At JPL, excitement grew as it got closer to the gas giant. Jupiter was visible through the spacecraft's cameras with never-before-seen clarity. A land with great storms and whirling clouds. For eons, the Great Red Spot was visible from Earth, and it eventually resolved into a complicated weather system that could engulf 3 Earths. As each new image appeared line by line on their monitors, scientists leaned forward in their chairs and gasped at details that had never before been seen to the human eye. After that, the findings came quickly. Astronomers had assumed that Jupiter's moon Io would be a dead, cratered world like our own moon, but Voyager 1 showed that it was actually alive with volcanic outbursts. The first active volcanoes ever seen outside of Earth were sulfurous plumes that ascended hundreds of kilometers above the surface. Just one discovery changed textbooks and broadened our knowledge of the solar system's geological forces. Voyager 1 proceeded to Saturn after Jupiter, reaching there in November 1980. Here, the actual intricacy of Saturn's ring was exposed by the spacecraft's cameras and equipment. Thousands of distinct ringlets with complex features, rather than the straightforward bands visible from Earth telescopes. The pictures revealed braided patterns that were difficult to explain and enigmatic spokes that moved through the rings. Scientists compared the experience of viewing these pictures to being in front of a magnificent piece of art, both visually pleasing and scientifically engaging. Titan, Saturn's largest moon, was especially fascinating. It was covered in a dense orange atmosphere that prevented Voyager from seeing its surface. Complex organic chemicals were found in this atmosphere by spectrometers, indicating that Titan may support chemical processes akin to those that gave rise to life on Earth. It set the stage for following missions like Cassini-Huygens, which would eventually uncover Titan's methane lakes and rivers, even though Voyager was unable to see through the cloud. During these planetary contacts, the control room was a controlled environment of excitement. Scientists and engineers bent over the console. Quiet talks punctuated by the repetitive clicking of keyboard keys. Cheers broke out when important photos arrived, and then there was heated discussion about unexpected features. There was a sense of discovery in the air. Global media gathered outside the facility, and pictures from these far-off worlds showed up on TVs and newspaper front pages all over the world, bringing the wonder of discovery into people's living rooms everywhere. Voyager 1's journey led it northward out of the plane of the ecliptic, the flat plane in which planets orbit the Sun, after it finished its primary mission at Saturn. It would not come across any additional planets on this route. Voyager 1's planetary exploration phase was over, but an even more remarkable trip was just getting started, while Voyager 2 proceeded on to Uranus and Neptune, the journey to the pale blue dot, interstellar space, and beyond. Prior to Voyager 1's cameras being permanently turned off to save power in February 1990, mission scientist Carl Schahn persuaded NASA to rotate the spacecraft for a last round of photography. Voyager took a series of pictures of the planets from 3.7 billion miles distant. One of these images showed Earth as a pale blue dot, hardly perceptible in the expanse of space, hanging in a sunbeam. One of the most profound images ever captured was the resultant image. Later, Schahn thought that this small pixel, our entire universe, represented our duty to treat each other with more kindness and to protect and value the pale blue dot, the only home we had ever known. The image humbled humanity's position in the universe by Parberton Berchumas, by Vorteres ba Ingenichudicum Zerfing des Genio, Phoebesis the Jutanium, the Orbis Mardil will be any. The image humbled humanity's position in the universe by Hemberges Dam, then the universe by Mildes National Day, so Safon the Barons of Man and so Sarandels Perception, the image ultim bestlution in the universe by whole, transforming scientific data into a philosophical viewpoint. Mission controllers ordered Voyager 1's cameras to shut down permanently after the portrait of the faint blue dot. The pedestal for the camera had done its job. In the future, particles and invisible fields would be used to follow the voyage instead of pictures. The shift from Voyager as a planetary explorer to Voyager as an interstellar pioneer was symbolized by this event. The radioisotope thermoelect electric generator, the spacecraft's power source, continued its unavoidable decrease, generating roughly 4 watts less electricity annually. Engineers likened it to a spotlight that gradually fades over many years. Nevertheless, they continued to decipher its light. They turned off heaters and other unnecessary equipment as part of their innovative power-saving strategies. Systems that were intended to run at cozy room temperatures now operated at temperatures close to freezing. Even the spacecraft's designers were taken aback by how resilient it was. Voyager 1's equipment documented the thinning of the solar wind, the stream of charged particles continuously flowing away from the Sun as it passed beyond the orbit of Pluto, which was still considered a planet at the start of the voyage. This area, known as the outer heliosphere, symbolized our star's diminishing power. Each signal was avidly examined by scientists looking for indications that Voyager was getting closer to the line separating the domain of our solar from the actual interstellar space. Since the rendezvous with Jupiter and Saturn, the rate of data downlink had dropped significantly. Voyager used to send planetary photographs and measurements at a rate of 115,000 bits per second, but today it only transmits at 160 bits per second, which is slower than the first home internet modem. Every valuable bit of information went billions of miles and was picked up by NASA's Deep Space Network's 70-meter dish antennas. These signals were so weak that they were measured in zeptos, or sextillionths of a watt, when they arrived on Earth. However, they contained vital information about areas of space that had never been visited by any human device. Voyager 1 resumed its stealthy outbound trip as the 20th century came to an end and the 21st century began, measuring particles and fields in more rare locations. Nearing retirement were the engineers and scientists who had started the project as young professionals. A few had already died. However, the spaceship they had constructed kept working, outliving some of its builders and extending the reach of humanity farther and farther into space, surpassing the limit. Voyager 1 observed a steep drop in solar particles and a substantial rise in cosmic rays on August 25, 2012. At the same time, a significant change in the direction of the magnetic field was observed by the spacecraft's magnetometer. These modifications represented a turning point in history. The helop, the point at which the interstellar medium ultimately gives way to the solar wind's outward pressure, had been traversed by Voyager 1. A man-made device had finally made it into interstellar space after 35 years of journeying. Months later, following thorough analysis, the confirmation was made. Similar to the first circumnavigation of Earth or the first steps on the Moon, the announcement in September 2013 marked a significant milestone in exploration. Since our race first looked at the stars, all human exploration had been confined within a solar bubble, but humanity has now expanded beyond it. Material from other stars, protons, and fields that came from far-off supernova explosions and stellar winds from across the Milky Way now surrounded Voyager 1. Because the electron density in this area was roughly 80 times higher than that inside the heliosphere, Voyager's instruments were able to identify unique plasma oscillations. Theories that had previously exclusively depended on mathematical models and astronomical observations now have ground truth thanks to these readings. Despite the predictions of many scientists, the interstellar medium turned out to be different. Our solar bubble and the surrounding galactic environment may have intricate interactions, as seen by the stronger and unexpectedly directed magnetic field. The sharp rise in cosmic ray intensity demonstrated how the heliosphere has been protecting our solar system from these high-energy particles. Models of this boundary region were improved with each additional data point. Information that would be essential for organizing upcoming interstellar travel and comprehending the interactions between our solar neighborhood and the larger cosmos. In ways that technical measures could not describe, the public's imagination was captivated by the journey into interstellar space. There was no physical marking to indicate the boundary, and it was invisible. However, it was a milestone of great importance. Humans had only ever traversed the immense distance between stars in science fiction before, but Voyager 1 had already left our cosmic neighborhood behind. The accomplishment was reported by news outlets around the world, and social media was ablaze with responses that ranged from philosophical contemplation to scientific enthusiasm. Naturally, there was no significant change in the spacecraft itself as it passed this invisible boundary. As it exited the sun's domain, it continued to fly steadily at roughly 38,000 miles per hour, or 17 kilometers per second, without accelerating or decelerating. The equipment that may provide us with the most information about this uncharted area were given priority, while its systems on board continued to carefully manage the limited power supplies. Voyager 1 pushed the limits of exploration and extended the presence of humanity farther and farther into space, adding 1 million miles to the gap between itself and home every day. Voyager's power system is its lifeblood, its heart of power in the dark. Voyager uses 3 radioisotope thermoelectric generators, RTGs, to turn heat from decaying plutonium-238 into electricity, in contrast to solar-powered spacecraft that operate close to Earth. These RTGs generated roughly 474 of electricity when they were first introduced in 1977, which was sufficient to run a number of light bulbs around the house. This had decreased to around half of that amount by 2023, with production dropping by roughly 4 watts every year. Mission controllers have had to make more tough choices regarding which systems stay operational as a result of the gradual reduction in available power. The procedure, which determines which instruments can be sacrificed and which are most valuable for present scientific aims, is similar to triage in an emergency room. The UV spectrometer on Voyager 1 was able to function at -110 degrees Fahrenheit, -79 degrees Celsius, which is significantly lower than its intended operating temperature, when engineers shut off the heater in 2011. Surprisingly, it kept working. The Voyager team operates in a unique setting that transcends technology generations within JPL's Mission Operations Center. Vintage technology that has been maintained, especially for communication with the spacecraft, sits next to contemporary computers and displays. At the time of Voyager's launch, several of the crew had not yet been born. Others have dedicated their entire professional lives to this one goal. They characterize the experience as taking care of an aging relative, appreciating its tenacity while also acknowledging its limitations. To maintain its antenna pointed directly toward Earth, the spaceship must roll every 6 months. This vital function requires valuable, non-renewable hydrazine fuel from thrusters. Although power limitations will probably stop the mission before fuel depletion becomes a serious issue, engineers predict that there will be enough fuel left for orientation control until about 2040. They have, in the meantime, put in place ingenious software updates that are sent over billions of miles, lowering the frequency at which thruster firing is necessary. Giant radio antennas in California, Spain, and Australia make up the Deep Space Network, which communicates with Voyager 1 for hours every day. After more than 21 hours of travel, the signals are so weak that they can hardly be distinguished from cosmic background noise. Meaningful information is extracted from seemingly static data using specialized signal processing techniques. By today's standards, the resulting transmission rate is excruciatingly sluggish. Less than 120 million times the speed of a typical residential internet connection, 160 bits per second. Notwithstanding these drawbacks, Voyager 1 is still producing useful scientific data. High-energy particles coming from outside our solar system are measured by its cosmic ray detector. The electron density of interstellar space is recorded by its plasma wave sensor. The magnetic fields that pervade the space between stars are monitored by the magnetometer. When combined, these tools paint a singular picture of a setting that is impossible to examine in any other way: the space that our solar system passes through on its orbit around the galactic center. According to calculations, Voyager 1 might keep sending scientific data until around 2025 or 2030, at which point there won't be enough power left to run both the communications and science instruments. The spacecraft will thereafter go silent, but it will keep traveling endlessly. Among the stars, a silent emissary from Earth, the first oddity. Long after many of the original crew members had retired or died, Voyager 1 started sending out unexpected signals 46 years into its mission. Buried in routine telemetry was a low-frequency hum that was different from anything the spacecraft's plasma wave instrument had ever recorded. The sound pulsed with mathematical regularity, rising and dropping at regular intervals, and occupied a small frequency. Spectrum. As Voyager 1 evaluated the interstellar medium's density, the finding happened during routine data collecting. Engineers initially thought there might be an instrument fault or interference. Hardware that was created in the 1970s and is used for decades over its intended lifespan may eventually develop peculiarities. They compared readings from various systems and performed diagnostics. Several NASA Deep Space Network receivers confirmed that the hum continued. The attitude in the control room changed from routine to alert. This pattern did not fit known forms of solar emissions, cosmic radiation, or instrument noise, according to experts who had been tracking Voyager's signals for decades. Either a hitherto undiscovered natural phenomenon or anything with intentional organization was suggested by its structured nature repeating at exact timing. The rhythmic pulses that were initially discovered from pulsars in the 1960s brought back memories for several of the team members. Before their natural explanation was found, they were initially referred to as LGM or Little Green Men. Radio astronomers, signal processing specialists, and plasma physicists made up the specialized analysis team that NASA formed. They contrasted the hum with databases of known cosmic sounds, including the emissions from distant galaxies, pulsars, and magnetars. There was no match. The properties of the sounds were inconsistent with theoretical models of interplanetary occurrences. Its consistency after several weeks of monitoring ruled out fleeting occurrences like as gamma ray bursts or distant supernovas. The scientists who created the project almost 50 years ago had not anticipated the new detection made by the aging spacecraft. According to team members, it was like getting a knock on the door when you thought the house was empty. It was an exciting and unnerving feeling. Humanity's most far-flung explorer, Voyager 1, had come across an unidentified object. The enigmatic shift in direction. Not long after the inexplicable hum was detected, investigators discovered something much more mysterious in the telemetry of Voyager 1. The spaceship was oriented somewhat differently. This slight but decisive shift in course happened without any orders from Earth. Evidence of thruster firings that mission control had never started was detected by Voyager 1's attitude control system. Engineers looked into the spacecraft's self-correction mechanisms right away. Maybe a command sequence that had been programmed decades ago had finally run. They looked at backup plans intended to kick in the event that the main systems malfunction. The maneuver was not explained in the spacecraft's programming. Voyager's orientation has changed little but noticeably as a result of the thrusters firing in a precise rhythm rather than the haphazard puffs that are indicative of a system malfunction. The precise direction of the modification was even more perplexing. The change aimed Voyager's now defunct camera platform at what appeared to be a barren area of space devoid of any known stars, galaxies, or other significant celestial objects. It appeared as though the spacecraft had turned to investigate something more closely after spotting something that was undetectable to Earth's most potent telescopes. There were other issues with the time. The fact that the course change happened just a few days after the enigmatic hum was initially noticed raises the possibility that the two anomalies are related. Were they related elements of the same phenomena or separate coincidences? It seemed improbable that two unrelated problems could have happened so quickly. Experts analyzed trajectory data at JPL's navigation center around the clock. Due to electrical equipment that had been operating nonstop for days, the facility had an odor reminiscent of coffee and ozone. Complex orbital mechanics computations and historical telemetry comparisons were shown on monitors. As each possible explanation was methodically ruled out, the team's expressions became more and more worried. Despite being minor, the course modification persisted in the weeks that followed. Instead of reverting to its initial orientation, Voyager 1 maintained its new orientation, suggesting a long-term change rather than a temporary error. This perseverance further complicated the riddle by ruling out a number of plausible technical answers. Patterns in the data suggested that whatever had led Voyager to modify its trajectory was a permanent alteration to its voyage into interstellar space. Another abnormality in Voyager 1's signal was discovered by data analysts as they proceeded to investigate the hum and course change. Subtle modulations, or changes in timing and frequency that followed identifiable patterns, were seen in the spacecraft's radio communications. Instead of being straightforward distortions brought on by interference from the interstellar medium, they seemed to be structured. Information that was incorporated into the signal itself. Visual plotting of these patterns showed symmetrical intervals, geometric ratios, and recursive sequences that were not likely to be caused by instrument mistakes or random fluctuations. As though something was reacting to or imitating the spacecraft's communications protocol, several sequences seemed to duplicate elements of Voyager's own signals. In order to rule out one-time abnormalities, the patterns recurred with minor modifications throughout several transmission sessions. To examine these signal modulations, NASA hired experts in artificial intelligence and cryptography. Sophisticated pattern recognition algorithms looked for correspondences with mathematical sequences, communication protocols, or known cosmic events. One particularly disturbing finding was that some signal patterns resembled parts of the Arecibo message, which was humanity's well-known radio broadcast directed at the globular star cluster M13 in 1974. There were conflicting interpretation camps among the scientific community. Some advocated for explanations based on nature. These patterns might have been produced by Voyager's electronics being impacted by an odd magnetic structure or plasma production. Others were unable to ignore the signal's apparent design. It appeared that the patterns were too complicated, too structured, and too persistent to be explained by well-known natural events. In exclusive scientific conferences and specialized periodicals, a more general scientific discussion took place. The discoveries could be explained by new models of interstellar medium dynamics put forth by theoretical physicists. Researchers from SETI carefully examined methods for assessing possible non-human communication. Skeptics created thorough assessments of how the appearance of patented signals could be caused by several system failures. NASA took a calm public position during these talks, characterizing the anomalies as inexplicable data patterns that needed more investigation. This meticulous wording belied true scientific confusion. The patterns required interpretation yet refused easy explanation. Universities and independent research groups from all across the world joined the study, using a variety of analytical techniques on the Voyager data that was made available to the public. What began as an engineering oddity was turned into a multidisciplinary scientific phenomena by this international scientific endeavor, which involved scientists from the fields of communication theory, mathematics, astronomy, and plasma physics. Regardless of what Voyager 1 had come across, its finding had sparked an incredible gathering of scientific expertise aimed at solving one of the biggest riddles in the history of space exploration, the legacy of Voyager. Voyager 1's anomalies marked the end of one of humanity's greatest exploration successes, regardless of whether they were caused by natural events, system failures, or anything more exceptional. For more than 4.5 decades, a mission that was initially intended to explore the outer planets for 5 years has persisted, revolutionizing our knowledge of our solar system and the area beyond its borders. The primary mission of the spacecraft produced groundbreaking findings, including as the unexpected diversity of Jupiter and Saturn's moons, the intricacy of Saturn's rings, and active volcanoes on Io. Our first direct observations of the interstellar medium, the space between stars that our entire solar system passes through, came from its prolonged mission. Voyager 1 continues to provide extraordinary data on parts of space that we cannot study in any other way, even as its power wanes and its systems age. Beyond its achievements in science, Voyager holds great cultural value. All other human artifacts are unlikely to outlive the message contained in the Golden Record, which is humanity's most remote and long-lived time capsule. By offering a viewpoint that cuts beyond national borders and serves as a reminder of our shared home, the pale blue dot snapshot altered our understanding of our place in the universe. A monument to human ingenuity and craftsmanship is even the spaceship itself, a technological holdover from the 1970s that continues to operate in the harshest environment imaginable. Even if the enigmatic signals and course changes are eventually explained by traditional means, they will have pushed scientists to create new theoretical models and analytical techniques, which will have advanced science. They could result in significant changes to how we think about interstellar space if they are actually new phenomena. Either way, exploration serves the fundamental goal of advancing human understanding. Long after its power supply fails and communications stop, Voyager 1 will still be traveling. It will pass within 1.66 light-years of the star GSA 445 in about 40,000 years if no additional course modifications are made. We'll journey among our galaxy stars for billions of years, perhaps even outlasting Earth itself, barring a very unlikely collision. One day, this stellar record might be the only proof that humans ever existed. In the dark, what did Voyager 1 find? Why did it alter its path? What caused its signals to exhibit patterns? There may never be comprehensive answers to these problems. However, by asking them and following this little explorer's voyage over unfathomable distances, we contribute to the great human endeavor of expanding our horizons. We are reminded by Voyager that there are mysteries and wonders in the universe that we have not yet figured out. Thanks for watching another episode. Please like and subscribe for similar content.